we're working on linear regression. We just barely started this example. So we learned that trips per second and temperature can be related through the following regression line. For y equals 26.346 plus 3.24x, and the error terms have a normal distribution with a variance of 0.94. So if we wanted to find the expected temperature when the crickets are chirping at 20 trips per second, we said that x is 20, and all we had to do was plug x equals 20 into our equation. Okay, and then what's our expected value for the dependent variable change when the explanatory variable increases by 1, which is basically just asking us for our slope. So if trips per second increases by 1, then we expect temperature to increase by 3.24 degrees. So now with that in mind, what would you do if I asked you how much does the expected value of the dependent variable change when the trips per second increases by 3? So if trips goes up by 3, temperature should go up by okay. If we plug 3 in for the x, then that will just tell us the temperature when trips is 3 trips per second. But we want to know how much should the temperature go up when we increase trips by 3 seconds. So no matter where you are on the line, how much do you increase in temperature if you go over 3 trips? Yeah, so you just have to do 3 times your slope. So instead of going over 1, you're just going over 3. So if trips goes up 3, no matter where we're on the line, we expect our temperature to go up by 9.7. Okay, if the trips per second is 0, what is the expected temperature? Okay, so we can plug in 0, or you can realize that this is really asking for your y-intercept, which is y equals 26.346 degrees. And that probably is a practical interpretation for a y-intercept. So on the previous page, I said sometimes your y-intercepts don't really have practical or logical interpretations. We just put it in so we can find our line. But I could see if there's 0 trips per second, then the temperature could be 26 degrees. For the next one, what is the probability that the temperature is below 70 trips per second? Oh, sorry, temperature is below 70 degrees when the crickets are chirping at 14 trips per second. Okay, so any thoughts on what you could do for this one? A little different than what we've done so far. Oh, the area under the line. Okay. What about I did, but we're actually going to go back to the fact that we said all of your y values at any specific x value, your y values are normally distributed with the expected value and the variance. So anytime what happens are normally distributed, we can go through and learn, use all of the things we learned about finding probabilities for normal distributions. Okay. So remember, if we want to use a normal distribution, then our formula is z equals basically x minus the mean over sigma. In this situation, okay, so that's our formula. In this situation, we have specifically a y value minus what would be the mean or the expected value. The expected value would be our beta naught plus beta 1 xi, and the standard deviation is the square root of the variance, so just sigma still. So basically, if you want to find normal probabilities or probabilities associated with the yi values, you can use this standardization formula. So for our situation, what is the specific y value that we're interested in? The 70. We want to know if it's below 70. Minus, let's see, beta naught 26.346 plus our slope 3.24 times our specific x value, which is 14 trips per second. All over the standard deviation, which is what? 0.84, how did you get that?
94 is just a subject in the problem statement.
Okay, well, and so that is our variance, our sigma squared, so we need to just take the square root. Remember 1.76? Cross our z square. Let's see, so we were looking for the probability that y was less than or equal to 70. Remember our given notation? I could write here given x equals 14. So we're looking for that probability. Really, now that's just the probability that z is less than or equal to negative 1.76. And at this point, all I have to do is go to our standard normal table and look up negative 1.76. And I did bring z and t tables up here if you want to come grab them. Let's see, so we're at negative 1.7. 1, 2, 3, 4, 5, 6. 0.0392. So then we got a 4% chance that we're going to get a temperature of less than 70 if the trips per second are 14. And just as a little side note, just because I'm curious, so what was the expected temperature for 14 trips per second? Okay. So to find that, then x equals 14, and all I have to do is plug it into my equation. So y equals, then 26.346. Plus 3.24 times 14. $71.76. So our expected temperature for 14 joules per second was 71.7. And apparently our points are close enough to the line that the probability that we actually get a temperature below 70 is only 4%. Any questions on this problem? Okay. So you know enough to do section 12.1? Yep, 12.1 for the homework, and the problems are just like this over and over again. The problems in the book. So next section is fitting the actual regression line. So in practice, we don't know the primary values, beta naught and beta 1. Just like we don't know our population mean and population standard deviation, usually we don't know our true parameters for our line either. So want to estimate our parameters by finding the best line to fit our data. Usually it's the data in our sample. Okay. Whereas our parameter values would still be for your population of all possible values. Okay, and once we have our best line, then we can compute our slope and intercept. So for example, we have natural gas companies place orders for the natural gas to be transmitted by pipeline to their cities. When they place their orders, the gas company makes its best predictions of the city's natural gas needs for the next period. And in order to control costs and things, the company charges you if you order too much or too little, but they do give you about a 10% leeway. So here's data for one city over 8 weeks. The data has the average hourly temperature and the weekly fuel consumption data. When you look at those two things, which one would make more sense to be the explanatory variable? Or which one would you probably be more interested in as the explanatory variable? Or which one would you want to predict if you're this gas company? You would want, you want to be able to predict the fuel consumption. That means temperature is going to be your explanatory. Okay. So out here, so how would you decide the best line? Okay. So for this data set, I've drawn the scatter plot. What would the best line look like for you? So everyone on your notes, draw on what you think the best line might be. Did everyone like the exact same best line as I did? Okay, so pretty close, so maybe it could have been something like this, or maybe something like this. Okay, that data set, we're probably all about fairly close lines. Okay, what about for this next data set though? Everyone draw on what you think might be the best line for this data set. So what did your lines look like? 3 people that want to come draw their lines up here. I can just pick the front 3 people. Sure, come draw your lines. Oh, you can come too, and then I'll draw mine. Yeah, I'll just on one of the spots. That's okay. It'll help illustrate my point. So, I mean, we might have trouble finding our exact best line just by eyeballing it. So then we have a more mathematical way to define our line of best fit. Okay, so what are some ways that you would think of that you could define your line of best fit? Okay, so come up with a mathematical rule that will make this the best fit. Just brainstorming. What are some of the things that you would be interested in looking at?
You want to minimize the distance from your point to your line.
Okay, so you want to minimize the distance from the points to the line. Okay, so how would you do that? I guess first you would measure the distance from the point to your line. Okay, then how would you go about minimizing that?
Probably have to put the line at the average of all your values.
Okay, you can try and put the line at the average of all your values. And then the way that does kind of end up happening. Let's see, so you said minimize the distance between your point and the line, but I have a lot of points here. So I also have this distance, and this distance, and this distance, and this distance. What do you think I should do with all those distances? Probably add them up. Okay, now what's going to happen if I just add up the distances as they are?
There's negative ones, and it's going to kind of wipe out.
So we square.
So we're going to square them. Okay. Now, people who invented this, instead of squaring it, they probably could have taken the absolute value, but they squared them instead. Kind of like variance, yeah. So, we decided, and this isn't the only possible way to do things, but the most common way that you'll ever find your line of best fit is called with squares. So for each possible line, you find the vertical distance between each point and line, you square them all, and add them all up. And we're going to call out our total square distances, and then you pick the line that has the smallest total square distances. So this is the line that our mathematics found for us, so it's pretty close to the lines we guessed by eye. Notice, anytime that you're going to be working with a linear regression, you actually find your line of best fit, you do have to have an explanatory variable and a response variable. So your response variable has to be on your y, just the way they calculate it. It would make a difference if you switched the two. You get a different equation. Okay. So when we're saying that we're minimizing the total square distances, the distance between each point in the line, remember we define that as the error term, epsilon. So it's each error term squared, and that's what you want to minimize. Or if you want to think about it, the error term is the y value minus the expected y value. So once we find our line of best fit, we can call it our regression line. So again, it's just a straight line, describes how our response variable y changes as the explanatory variable x changes. And we can use it to predict our value of y for a given value of x. And this is the equation for the line that we'll use. So we have y hat equals beta naught hat plus beta 1 hat x. Why do we use all the hats? Yeah, to remind ourselves that we are estimating that. So anytime we're estimating something, we'll put the hat on it. So y hat is our predicted y value. Now there are two possible interpretations, and you'll see this as we go built into some examples. But you could think of y hat as the predicted individual y value for your specific x value, or you could think of that as the predicted average y value for the given xy value. So let's say we were looking at this data set still. Let's say we have a temperature of 50 degrees. I could plug 50 into my equation and get my answer, and I can either interpret that as the field I will need next time it's 50 degrees, or I can interpret it as the field that I will need on average for all weeks that have 50 degrees. So you can interpret that either way. Again, beta hat naught would just be our estimated intercept, beta hat 1 estimated slope. Okay. Now, sigma hat squared is the estimate of our error variance. And as you do your homework, your book will commonly ask you for the estimate of the error variance, and that's what they're looking for. Also called mean squared error. Okay. And it can be thought of as kind of like an average of your squared residuals. Okay. And we use software to find our mean squares regression mean. You can see your book, page 555 for the actual formulas if you want, but we'll again never calculate those by hand. Again, we've already talked about the error. So it's just the difference between the predicted value and observed value. So it's always observed minus predicted. And extrapolation. So extrapolation happens when you try and predict for x values that are outside of the original data set. So if your data set only goes from like 30 to 40, you shouldn't try and predict for x values of like 100. Okay? And the reason you don't want to use extrapolation is you can't guarantee that your relationship continues past that point. Because if you have a data set that looks like this and fairly close to a straight line, and you get to a certain point, and what could happen? So if you go up and then like die off, or if you go up and then you could hit like your carrying capacity, things like that. So you can't guarantee that your linear relationship continues past a certain point. Now, does that mean that people never use extrapolation in practice? Okay. No, lots of times it's the best information you have, and some information, even if it's inaccurate, might be better than no information. But you should keep in mind as you do this that anytime you're extrapolating, your answers might not be accurate. So for example 10, using intercept, we can find our least squares regression line for the fuel consumption example. The mean square error is 0.4280. So remember, mean square error is another, just the way to write sigma hat squared. It's 0.4280. So that's just our estimate for the variance of the errors. So what is our linear regression model, or our regression line? Okay, and these ones are really easy because you can just read it off the graph. Okay, so using the y hat equals negative 0.128x plus 15.838. Notice they did change the order. They wrote the slope and x instead of intercept first. But at this point, after taking calculus, hopefully you can still recognize which point is your slope. Okay. So what is beta hat naught? That is our intercept. In this case, it is 15.838. Okay. And how would you interpret that? What does it mean to us?
Would that be the maximum fuel needed?
Could we possibly have a negative temperature though? Because then we never get to negative temperatures.
Yes.
Okay. So
that's the fuel consumption predicted at 20 degrees.
So it's not even at 20 degrees, so people don't do that a lot when they look at my plot, because my plot only went to 20 degrees. But mathematically, our intercept is always when x equals 0. So it's always the y value when x equals 0. No matter what the graph looks like, that's our definition of an intercept. So if the temperature is 0, we expect to use 15.838 units of fuel. Now, of course, that can vary from week to week, but that should be the average in the long run of how much we use when it's 0 degrees. Now, beta hat 1 is our slope. So our slope in this case is negative 1.28. Oh, no, it's negative 0.128. And we always interpret slope as rise over run. So this means if temperature goes up 1, we expect fuel consumption to, let's see, since it's a negative slope, so we expect it to decrease by negative 0.128 units. Which makes sense, right? The hotter it gets, the less you need to run your heater. So, any questions of this book? So what if you want to predict your weekly fuel needed if the temperature is 39 degrees? What would you want to do here? Just plug in 39 degrees for x. Simple enough, right? So y hat is negative 1.28 times x 39 plus, okay, 15.83. And what did you say about?
Well, it's negative 20.
Oh, yes, thank you. I keep adding that. I even type it. So 10.846, that's the predicted mean. Now I want you to find the residual for week 4. You can only find the residuals if you have your actual data set, but I did give you the actual data set for this one because it wasn't very big. So for week 4, notice our temperature is 39 degrees, very convenient since that's what I just asked you to predict. And the actual fuel needed was 10.8. So our predicted y hat was 10.846, and our actual y value was, what did I just write off? 10.8? Okay. So look back up at the previous page. What is our formula for our residual or our error term? Instead of epsilon I can actually write this as epsilon 4 because that's my error for the 4th week. And what is my formula for that? Observed minus predicted, so the actual observed. So 10.8 minus my predicted, 10.846. It's negative 0.046. So our prediction was just a little bit high, but not too bad. So same thing, if I want to predict the fuel for the temperature of 57.8 degrees, then x equals 57.8. And all I have to do is plug it in. .4396. And then I've asked you to find the residual for week 6. So, flip back to your previous page. What was our x value for week 6? For week 6, our temperature x value is 57.8, and our observed fuel is 9.5. So we have our observed. Because that's the same x value we just found a prediction for, we have our observed and our predicted. And then to find our error term, this is the error term for the 6th week. Again, it's just observed minus predicted. So observed is 9.5 minus our 8.4396. So this time our residual, how far we are off, was 1.0604. And I told you to look at the scatter plot so you can kind of see. So we had our weeks, I think 1, 2, 3, 4. Notice on week 4 how close the point was to the line, and that was when we found a really small residual. And then 5, 6. This was week 6, where again we had that really big residual, which is why it's really far from the line. And predict the fuel needed for the temperature, if the temperature for the week is 93 degrees. So in this case, we have x equals 93, and we just plug it in. And then plug it in, I get 3.934. However, if I come back up and look at my actual data set, what is my temperature range? Yeah, we're looking about 28 to 62.5. So our 93 degrees is somewhere over here. So can you guarantee that this relationship holds? Okay. And at 93 degrees, do you turn on your heater at all? Hopefully not. Okay. And so I think that this value might have been extrapolation. So, but this would be extrapolation and probably inaccurate. And in fact, if I took my temperature up even more to say like 100, not high enough yet. Oh, okay. If I go all the way up to 130 degrees, so here in the middle of the desert, we actually get a negative fuel consumption. And at that point, are they ever going to start like just doing fuel for no reason? The negative fuel consumption? Probably not. So you can see if you go far enough up, sometimes you also get unrealistic answers, like negative fuel consumption, things like that. But even at 93 degrees, we don't think we should be using any fuel consumption, so this probably was extrapolation. Okay. And finally, what was our estimate of our error variance? So we asked for the estimate of the error variance. That's just sigma hat squared, and we wrote that down on the first page. Let's see that our mean square was 0.4280, and I'm telling you that's the term for the estimate of the variance of the errors. So just 0.4280. So that should be the really easy question on your homework, because all you have to do is read it off. Just reading off the problem, so right here where it says the mean square error. Whenever you see that, just know that that is your estimate of sigma squared. As far as your homework, because I didn't want you to have to do these formulas by hand, for section 12.2, when you go on, you'll see that there's a PDF with helpful computer output for you, so you can just use the computer output to do all your homework. And it will be similar for the test. So any questions on how we're doing anything here? We have one more problem, just to make sure there's something. So what is our equation? Oh, I guess we should start the problem. Let's see, so we're going to study the relationship between X, which is home value in thousands of dollars, and Y, which is yearly expenditure on home upkeep in just dollars. Data is collected on a random sample of 40 homeowners. Using NextStat, we can plot the equation, plot the data, find the equation Y, and find that our mean square error is 21,578. So looking at this, what is our equation for our linear regression model? So we have y hat equals 7.258x minus 348.392. Has anyone noticed, and this one on the last one, how there's that R squared on there? Okay, we're not going to do R squared, go over or use it on our homework at this point, but remember how we had R squared for our ANOVA? We also have R squared from linear regression, and it has a similar but slightly different interpretation. So overall in statistics, R squared always tells you basically how well your model is going to be at like describing your data. So if we have an R squared of 0.889, then that basically tells us that our model, or our line, can explain about 88.9% of the total variation in our Y values. And the rest of the variation would just come from the natural variation from person to person. So if our line can explain 88.9% of the variation in the Y values, that's pretty good. We can make pretty good predictions with it. But just a side note there. So we have our linear regression model. Okay. What is beta not zero? Interpret it, and does this have a practical interpretation? So that is our intercept, which is negative 348.392. Now remember, the definition for the intercept is always your Y value when your X value is 0. So this would be something like if home cost, or if the home value is $0,000, which is still just $0, we expect the upkeep cost to be negative $348.392. Okay. Does that have a practical meaning to us? Okay. No, last time I checked, if you don't have a home, no one gives you back money for the upkeep of your non-existent home. Okay. Anyone on money department just gets a check every month from now for that amount? Yes. Okay. So lots of times, so we say this at the beginning, I still need that y-intercept to be there because it makes my line fit my data better. If I'm trying to move my line over so that it went through the point 0, 0, then it wouldn't fit my data as well. Okay. So we still make the intercept what fits our data the best, but it doesn't always have a practical meaning. However, in case you're wondering, our slope should always have a practical meaning. It's just that intercept is sometimes a little screwy. And when I ask for beta hat 1, and for you to interpret it, beta hat 1, that would be my slope again. And my slope at the moment is 7.258. And how do we interpret our slope?
For every $1,000 of house value increase, upkeep increases by $7.26.
Okay, and so it's good that you remember that our units were thousands of dollars, so it's not for every $1 increase, it's for every $1,000 increase. So for every $1,000 increase in home value, we expect a $7.25.8 increase in upkeep. And then on home, I get to experience the joys of home upkeep. Notice? Apartments are easier. The homes are nice too. Okay, so let's predict the upkeep for John's home that is valued at $22,000 or $220,000. So what do we need to do here? Okay, divide 22,000 by 1,000 to get our actual x value, so our actual x value in this case is just 220, and then I just need to plug it into our equation to predict it. So 1248.368, and that should just be in dollars. So we predict that for John, when he has a $220,000 home, he's going to have to spend about $12,000 a year on upkeep. Okay, now what's the difference between that question and then for 5, predict the average upkeep for all homes that are valued at $220,000. Okay, notice a slightly different interpretation. Do I have to do anything different? Okay, no, it's the exact same thing. X equals 220, and we just plug it into our equation just like we did for John's single home. So we predict it the same way for both interpretations. Now, which prediction do you think might be more accurate? The average should be more accurate because John might be a little bit higher or lower, but when you do the average, you have all those people that are a little bit higher or lower, and they should average out to be a lot closer. So your predictions for averages will always be more accurate than your predictions for a single person. And if I asked you to predict the yearly upkeep for an individual home worth $1,500,000, we would start the same way. So X equals 1,500. And what do you feel about that 1,500? Okay. If you look back at your scatter plot, so we'll go to about 300, 290, something like that. So where is my 1,500? Right out here. And can you guarantee that that linear relationship continues all the way up to our 1,500? No. So this would be extrapolation. You can predict it if you want. But it is probably inaccurate. Any questions? In that case, take your 2-minute break and we'll start our next section.